All right, let's jump right in. We are going to pull back the curtain on one of the coolest, most futuristic pieces of tech you can have in your kitchen. You know, it really feels like magic, but today we're going to break down the brilliant science that makes it all work.
So, here's the big question, the central mystery we're going to solve. Just picture this, a stovetop that's on, cranked to full power, but you can put your hand right on the surface and feel, well, pretty much nothing. And yet, the second you place a pan on it, water is roaring to a boil. How is that even possible? It sounds like it defies the laws of nature, right?
Well, as you probably guessed, the answer isn't some kind of sorcery. It's actually a super clever and, honestly, elegant application of some fundamental laws of physics. And to really get it, we need to rewind the clock a bit, back to a huge discovery made almost 200 years ago. Okay, first up, the magnetic magic. Before we get into the how, let's just take a moment to appreciate the phenomenon itself and what makes it feel so impossible.
This is the thing that just messes with your brain, isn't it? The stovetop itself stays cool, but the pan on top gets screaming hot, and it does it fast. It just seems to go against everything we think we know about heat. But that's exactly what makes induction so revolutionary.
So, to crack this puzzle, we've got to look at the invisible forces that are making all this happen. Let's dig into the key scientific principles that unlock the whole mystery. Our first and most important clue comes from the brilliant Michael Faraday. Way back in 1831, he figured out that if you have a magnetic field that is constantly changing, it can actually make electricity flow, an electric current, in a piece of metal nearby, without ever touching it. This one idea, right here, is the bedrock of everything we're talking about. Now that word changing in Faraday's law is everything. A regular old magnet just sitting there won't do a thing. You need constant change. And that's where alternating current, AC, the stuff that comes out of your wall sockets, comes into play. It's constantly flipping its direction back and forth, which creates the perfect, rapidly oscillating magnetic field we need.
So we've got a changing magnetic field, but how does that make a pan hot enough to cook an egg? Well, this is the craziest part. The stove doesn't actually heat the pan. Nope, the pan literally heats itself.
And the way it does this is through something called eddy currents. When that magnetic field from the stove passes through the metal of the pan, it creates these tiny, swirling, circular currents right inside the metal itself. It's Faraday's law in action, right there in your cookware.
I absolutely love this description because it gives you the perfect mental image. Don't think of electricity flowing in a straight line. Instead, picture countless little whirlpools of energy just spinning like crazy inside the bottom of your pan.
So how do these little whirlpools actually make things hot? It's a process called Joule heating, and it's pretty straightforward. First, the magnetic field creates those eddy currents. Then, as these currents try to swirl through the pan, they run into the metal's natural electrical resistance. You can think of it like friction for electricity. And that friction, that resistance, converts all that electrical energy directly into heat. And just like that, the pan gets hot from the inside out.
Okay, theory time is over. Now let's get practical and take a look at the anatomy of an induction cooktop to see how all these principles are actually put to work.
You've probably heard you need special pans for induction cooking, and this is exactly why. The pan has to be ferromagnetic, basically made of something with iron in it. These materials are amazing at grabbing and concentrating the magnetic field, which makes those eddy currents way, way stronger and more efficient. Plus, they add a second source of heat called hysteresis loss. All that means is the magnetic particles in the pan are flipping back and forth so fast that they create their own heat from friction. It's why the old magnet trick works. If a magnet sticks firmly to the bottom of your pan, you're good to go. And this, right here, is the solution to our original puzzle. It's so simple and so smart. The glass ceramic surface of the stove, it's an insulator. The magnetic field just passes right through it like it isn't even there. No current, no heat. The pan, on the other hand, is a conductor. The field goes into it and whips up those powerful eddy currents, generating a ton of heat right where you want it. The energy skips the stovetop entirely.
So, with all this incredible physics packed inside, does that mean induction is truly the kitchen of the future? Well, let's zoom out and look at the practical side of things.
The pros are really compelling. It's wildly energy efficient, it cooks faster than gas or electric, and it's so much safer because the surface stays cool, which is a huge deal if you have kids or pets. And the temperature control is instant. But, there are trade-offs. The upfront cost is still a bit higher, you absolutely need the right kind of cookware, and yes, sometimes you can hear a faint humming sound, especially on the high settings.
But let's go back to that number one pro for a second. Efficiency. An induction stove converts about 90% of its electricity directly into heat in the pan. Let that sink in. 90%. That is just a staggering number.
And this chart really just puts it all into perspective. Look at that. With induction, almost all the energy you're paying for is actually cooking your food. A traditional electric coil is okay, at around 75%. But gas? Wow. Only about 40% of the energy from that flame is actually heating your food. The rest is just wasted heat, making your kitchen hot. The difference is absolutely massive. So in the end, the magic isn't really in the stove at all. It's in that incredible interaction between the stove's magnetic field and the pan itself. It's such a cool reminder that our world is just humming with these powerful, invisible forces. Which leaves me with one last question for you to think about. What other invisible physics is powering all the technology that you use every single day?